Hi, welcome to the Olympiad Geometry Club. Let's continue our study. Today we're going to talk about the IMO 2026, this year IMO problem. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. Let's start. Let ABC be a triangle, and let points M and N be the midpoints of sides AB and AC. So we have A, B, C here. We have midpoint M and N. Respectively, let points K and L be chosen inside the triangle BMC and BNC. So we have triangle BMC and BNC. Somewhere we have K, somewhere we have L. And such that K lies inside the angle LBA. For example, L is here, then LBA is here, K is inside here, and L lies inside the angle ACK. So ACK is here, L is here, right? And angle KBA equals to angle ACL. So for example, K is here, KBA, we want this angle. The angle KBA equals to angle ACL equals to angle ACL. Right? We want this angle equals to this one. Let's say this is L. And so angle KBA equals to angle ACL and angle LBK equals to angle LNC. So we want this one equals to this one. And angle LCK, we want this one equals to angle BMK. We want this angle equals to this one. Let O be the circumcircle center of the triangle AKL. So we have the triangle AKL here, and we find the circumcenter O. We want to prove that OM equals to ON. Roughly say this is a problem set. So first we need to find the KL. Right? Just draw a figure like this, you will never find KL properly. So for this kind of problem, I hate the way they gave the problem set because it's just a little tricky thing. It's not a big deal. For the IMO problem, I think they don't really need to do these small tricks. It's nonsense. Okay, let's just start. Look at, let me show just this one. So let me adjust this a bit. Okay, actually we don't really need the bottom half. Okay, just this is enough. So where do we start? Actually, let's start with this problem set that angle KBA equals to angle ACL. Okay, so if we just draw the triangle ABC here, and we know that we have a point that angle KBA equals to angle ACL, right? This is L, this is K. That means if we extend the BK and CL, we can get the figure like this. We know somewhere is K somewhere is L, right? And we still maintain that angle KBA equals to angle ACL, right? That means these 4 points are cyclic, which means we can use another way to find the line BK and line CL, which is here. We just find an arbitrary point D on side AC, and we do the circumcircle of the triangle BDC. This circumcircle meets AB on the point E, right? Then we know that K is somewhere on BD, L is somewhere on CE. So it ensures that angle KBA equals to angle ACL. And what else we want to have? We want to have angle LBK equals to angle LNC, angle LCK equals to angle BMK, right? So just imagine that we have L here, for example. Then we want angle LNC equals to angle LBK. Angle LNC equals to angle LBK. LBK is angle LBD, which means ND, LB are cyclic, right? ND, LB are cyclic. Also, we want the angle LCK equals to angle BMK. K is somewhere here. We want LCK, which is angle ECK, right? LCK. This angle equals to angle BMK. So we want this angle equals to this one. And look at the quadrilateral MKCE. If this angle equals to this angle, then we know that MECK is these 4 points are cyclic, right? Which means we can construct we can find the KL by just doing the circumcircle of the triangle BND, which intersect CE on the point L. And we can do the circumcircle of the triangle CEM, which intersects BD on the point K, as shown here. Right? Now we just finish our problem set. We find the point K and L. And the question is that we want to find the circumcenter of the triangle AKL, and that is O, and we want to prove that OM equals to ON. So let's just hold on the question here and just think about what we can get from this figure. Right, this figure already tells us a lot of things. The first thing we know is that M and N are the midpoints of AB and AC. And then just look at this figure, we can get what kind of information we can get. We know that M, B, C, D are cyclic, right? So the power of A to this circle BDC would be equal, which means AM times AB equals to, AE times AB equals to AD times AC, right? Let's just write it down here. AE times AB equals to AD times AC. That's the first thing we can get. And if you look at this circle, the circle BDN, we have AF times AB. AF times AB equals to AN times AD. And for the circle MEC, we have AE times AM equals to AG times AC. Right. If you look at these three equations, they are so similar, which means we need to find the relationship between all of them. Let's just look at this one. AE times AB equals to AD times AC. Right? That's basically for the points B, E, D, C. And what are the rest? Rest would be the point. Let's just look at the point, right? First one is B, E, D, C, and the second one would be B, F, N, D. So B, F, N, D. Now we bring F, N, D here, and the next one would be A, E, M, G, C. E, M, G, C. Which means we want to find the relationship between M, E, F, G, N, D. Now, if you look at the figure, we know that angle BEC equals to angle BDC. Right? Angle BEC equals to angle BDC. So the angle BF, the angle BEC equals to angle BDC, and because BF and D are cyclic, right, on this circle. So the angle BDC also equals to angle BFN. Right, because BFND are cyclic. So the angle BDC equals to angle BFN. And the angle BEC is actually the angle MEC. It equals to angle MGC because MEGC are cyclic. MGC. Which means we just get that angle MFN equals to angle MGN. So we get angle MFN equals to angle MGN. Which means MFGN are cyclic. So from here, what we can get is AF times AM equals to AG times AN. Right, that's all we have. Now look at the equation here. We have AF times AB. This one. AF times AB equals to AG times, AF times AB equals to AN times AD. And we also have AF times AM equals to AG times AN. We put them together. We notice that AM is half of AB, right? AM is half of AB, and AN are equal, which means if we use the top one divided by the bottom one, we get AM to AB equals to AG to AD, which equals to 1 to 2. That means G is the midpoint of AD. So if we put this equation, AG times AN equals to AF times AM, and this one together, we can use this one divided by this one. We have AF to AE equals to AN to AC, which means F is a midpoint of AE. Now we get that N is a midpoint of AC and F is a midpoint of AE. So we know that Fn is in parallel with EC. Right, that's all we can get right now from this figure. Again, we don't know how to use these conclusions yet, but we just try to find as much as possible. That's the way how we solve the problem. So if we just refresh our mind, now we get something like we know that AF times, we know that F is a midpoint of AE and M is a midpoint of AB. G is a midpoint of AD and N is a midpoint of AC. So if we look at what we have here, that will be interesting because AF times AB, right? AF times AB can be rewritten as twice of AF times half of AB, which equals to AE times AM. Right? And AE times AM equals to AG times AC. Which equals to no, let's just stop here. So we get AF times AB equals to AG times AC, right? AF times AB equals to AG times AC, which means AF times AB is a power of A to this circle, and AG times AC is a power of A to this circle, and they're equal. That means A is on the radical axis of this circle and this circle. And these two circles already have this point and the intersection on these 2 points. That means these 3 points are linear. I mean, these 3 points are collinear, right? Okay, that's what we can have for now. So let's just make a brief conclusion of what we have already. We just get the conclusion that F is a midpoint of AE, G is a midpoint of AD, and we know that M is a midpoint of AB and N is a midpoint of AC, and we also know that A is on the radical axis of this left, the circle BND and the circle CME. Now we want to think about what we can do the next. The next is kind of we need a little experience because we already have the knowledge that A is on the radical axis of this circle and this circle, right? So we know that A and this point and this point, these 3 points, see, these 3 points are collinear. And also, if we look at this circle, let's call this point as U, right? Because we already know that B, E, D, C, these 4 points are cyclic. So we know that triangle EUB and triangle DUC are similar, which means EU to UD equals to BU to UC. Or we can see that EU times UC equals to BU times UD. Okay, so EU times UC equals to BU times UD. What is BU times UD? That is the power of point U to the left circle. And what is BU times UD? Sorry, EU times UC. That is the power of U to this circle, the circle CEM, which means U is a point has the same power for the circle BND and the circle CEM, which means U is also on the radical axis of these 2 circles. That is saying these 4 points are cyclic. Sorry, these 4 points are collinear. Right? We have it like this. Okay, now the problem is interesting because we already know that this U is on the radical axis of this circle and this circle. And also, if we look at this circle, the circle BDC, okay, the circle BDC and the circle BND, right, these 2 circles. We know that U is on BD, and BD is the radical axis of these 2 circles, right? BD is the radical axis of these 2 circles. And also, for the circle CME and the bottom circle BCD, we know that U is on the CE, and CE is the radical axis of these 2 circles. Which means U is a very unique point. It's on the radical axis of these 3 pairs of the circles, right? So the power of U to all of them should be equal. Then we can just think about to extend this one, right? Because it's a radical axis, we don't know the relation of that, so we just extend it. Remember what we have. What we have is F is a midpoint of AE and G is a midpoint of AD. So if we look at this circle, the circle CME, we know that D is inside of this circle and GD would be part of the chord of this circle. So which means we can think about GD times DC, right? GD times DC is a power of D to the circle CME. So GD times, we just have this one, GD times DC, right? And it equals to KD times, let's call this point as I, KD times DI equals to KD times DI. Right, GD times DC equals to KD times DI. So what is GD? GD is half of AD. So if we rewrite this one, we can say it's half of AD times DC equals to KD times DI. Which means we can rewrite it as AD times half of DC equals to KD times DI. Then half of DC, we can just find the midpoint of DC. Let's call it point T. That is sin AD times dt equals to KD times di. So we get AD times dt equals to KD times di, which means AKTI, a cyclic. Right, we just get AKTI, a cyclic. Use the same method. Let's call this point H. We can say that AL, let's call the midpoint as SH would be cyclic, right? ALSH, ALSH, a cyclic. That's exactly the same. It's just not on dg times dc. It's on EF times EB, right? EF times EB equals to EH times EC. And EF times EB can be written as AE times ES. So we know that AE times ES equals to EH times EH times EL, which means ALSH, a cyclic. Okay, so now we have AKTI, a cyclic, and ALSH, a cyclic. Now we look at, basically we have the feeling that all of them are on the same circle, but we just need to find a way to prove, right? So we have AKTI, we have ALSH. The only same point here is A, so we need to find some relationship between other points. If we look at point B, we know that BS times BA, right? I'll just write it here. BS times BA equals to twice of BS times half of BA, which is BM times BE, right? BM times BE equals to BK times BM times BE equals to BK times BI. Right? So we know that BS times BA equals to BK times BI, which means SKIA acyclic. So SKIA acyclic. Now we can see AKI determine the circle, and S is on 8, T is on 8. Right? So one second. Yeah. So ATI determines the circle. We know that S on 8. Let me write it here. So ATI determines the circle. ATI determines the circle, and or AKI determines the circle, whatever, right? So we know that ATKI are on 8 and S is on 8. So we know that, let me see. So we know that ATIKS are on 8. And for here we have ALSH. Okay, yeah, we have ALSH, and then we can use the same way we can prove that LTAH, right? LTAH are cyclic. So we know that ATL here, wait, no, should be ATLH, right? ATLH. So ALSH, sorry, S should be here. ATIKS and LH, right? ATH on 8. So we know that basically TLIAHSK, all of these points are on 8, which looks like this one. Right, I just rewrite it. So let me rephrase it. AHSKLTI, all of them are on the same circle. And now we have O is the center of this circle. Now let's think about how we prove that OM equals to ON. Because O is inside of M and N are inside of this circle, so we can just think about how can we calculate the power of M to this circle and power of N to this circle. Because AHSKLTI are cyclic, so we know that the power of M to this circle would be MS times AM. Right, MS times AM, which equals to AM times, what is MS? MS is BM minus BS equals to AM times half of AB minus twice of BS would be BE. So it equals to AM times AB minus BE, that is AE, so half of AE, which equals to AM times AF. So it turns out that the power of M to this circle, the circle O, would be AM times AF times AM. And the power of N to the circle O would be NT times AN, right? NT times AN equals to AN times, what is NT, right? NT would be I'm just thinking about this one. NT would be Cn minus Ct equals to An times half of AC minus twice of Ct, Cd, right? So it equals to An times half of AC minus Cd, that is Ad. So it equals to An times Ag. And we already know that Ag times An equals to Af times Am. Right? So because M, F, G, N are cyclic, so we know that these two are equal, which means the power of M to O equals to the power of N to O. So we get OM equals to ON. And for now, it's just we just prove this problem, and I think we can expand this one, which means that we can actually calculate for the power of F to O, which is AF times AS, right? AF times AS. No, not AS, FS. Right? AF times FS. Notice that the MS is actually AF. Right? MS actually equals to AF. That means AF can be, let's say this way. We want to calculate for AF times FS. And because MS equals to AF, that means AM equals to FS. So AF times FS equals to AF times AM. So you can see this one and this one, they're equal, which means the power to the F, the power of F to circle O equals to the power of point M to circle O, which means OM equals to OF. So now we know that OM equals to OF and equals to ON. Similarly, we can prove that it equals to OG, which means O is the center of the circle AKL, and it's also the center of the circle FMNG. Okay, which is here, and so we're actually expanding this problem set, right? Now, if you look at the full figure, I still have something I want to prove. Okay, we already proved that MFGN, the center of MFGN and the center of AKL is the same point O. And now let's prove that MPLE are cyclic. Okay, MPLE. I want to prove that MPLE are cyclic. So this is actually very easy because B is on the radical axis of this circle, the circle CME and the circle AKL. So we know that BPBL is a power of B to the circle of AKL, right? BP times BL. It equals to BK times BI, and it also equals to, because it's on the radical axis of this circle and this circle, so it equals to BM times BE. So BP times BL equals to BM times BE. That means MPLE acyclic, right? MPLE acyclic. Now I want to prove that this point, the point of AL, so AL meets this circle, right? The circle BND on this point. Let's call it V. I want to prove that the point V is also on the circumcircle of BPLE. So first of all, we can see that AN times AD equals to AV times AL. Right? AN times AD equals to AV times AL. And AN times AD can be rewritten as twice of AN, half of AD, which is AC times AG equals to AV times AL. So it turns to be AG times AC equals to AV times AL, which means GVLC acyclic, right? And we still want to prove that, let's see. Yeah, so we have AV times AL equals to AC times AG. And we know that AC times AG equals to AE times AM, right? That's the power of A to this circle. So it equals to AC times AG equals to AE times AM. So we got AE times AM equals to AV times AL, which means MEVL acyclic. We know that MEPL acyclic, so we just prove that MEVLP acyclic. Okay, MEVLP. These 5 points are cyclic. And we also proved that GVLC acyclic. And actually, because V is, if you look at this one, Fn is in parallel with EL, and F is a midpoint of AE, which means that this point, let's call it Z. Z would be the midpoint of AL, right? Z would be the midpoint of AL. So if we calculate for AG times AN, it is AG times half of AC, right? AG times AN is AG times half of, because AN is half of AC, so it equals to AG times half of AC. And AG times half of AC equals to AV times half of AL, right? AV times half of AL. And Z is the midpoint of AL. So it equals to AV times AZ, which means AG times AN equals to AV times AZ. So that means GVZN are cyclic. Right. Or we proved that on the right side of the AX would be same on the left side of AX, right? We have the similar property on that side. I just don't mark it, but the property would be the same. And let's keep digging this one. What else we can have here? Actually, let me put this one as a homework if you are interested. Please prove that GV, so AL meets the circle BCD on this point. Let's call it A1. So please prove that GV A1D are cyclic. Okay, we just proved that GVZN are cyclic. Please prove that GZA1D are cyclic. Right, GVA1D are cyclic. And also you can get that Zn is actually in parallel with A1D. Actually, this figure we can dig more things on this region, PRQ region. It's just would be very lengthy if I keep talking. So I'll just stop here. Let's just review what we have in this problem. First, we find the way to construct the figure and find the point K and L. And then we try to find the relationships based on the figure. Basically, it's just calculate the power of the point to the circles. And then we find the radical axis point, and it's a point that's on the 3 radical axis, which make us to find the points are cyclic, right? And then the key point would be that we eventually find A, H, S, K, L, T, I. All of these points are cyclic, and then we can directly calculate for the, because we already have we know that these are the midpoint of BE and CD, so we can easily calculate the power of M to the circle O and power of N to the circle O to prove that they're equal. That's the problem, and then we can expand it to saying that the circle MNGF and the circle AKL share the same center, and we have some other properties we can prove. Okay, so for this problem, I don't think it's a very easy one, but in my opinion, it's not a very difficult one because it's actually just using one kind of knowledge, the power of point to the circle. It's just reuse it in many ways. Just try to find the power of different points to the different circles and list the equations. So I don't think this can be a, I mean, traditionally we say a very difficult problem, because when we say a very difficult problem, you might need to have different tricks in one problem. But for this problem, it's just the same trick. You just do the calculation. Okay. I don't know the response of candidates. I mean, also I don't know how people respond of this problem, whether they feel it's difficult or not. But personally, I think it's not a very good problem for the IMO. I would say it's, I mean, it's just a one trick. I want to see some problem have like different tricks. You need to think about different ways, look at the problem from different perspective, and then try to figure it out. That would be a good problem. But for this problem, it's not like that level. Anyway, I hope you like this video. See you in next one. Thank you.